Hello, students. This is part 2 of chapter 7, and there are 3 really key concepts to pay attention to. That includes Markovnikov addition to alkenes, hyperconjugation of carbocations, and carbocation rearrangement. So pay attention closely when we get to those sections. So the first type of alkene addition reaction we're going to talk about is the hydrohalogenation, adding a hydrogen and a halogen across the double bond. So this is going to occur where you break the double bond, you add H and Br. Here we're not showing the H because we showed the bond line drawing. Doesn't matter where the H and Br add. In this case, it doesn't matter because you'd end up with the same sort of product if you flip the molecule over because this is symmetric. But when it's asymmetric, it does matter. And what we're going to find is we add the H to the less substituted carbon. So you have a double bond. We call these vinylic positions because the double bond is a vinyl group here. And so you're going to add the H in a Markovnikov fashion where you add the H to the less substituted position. Here I'm showing on the left side, there's a H and a methyl versus 2 methyl group. So you'll add the H across the double bond on the left. So when you add it here, it's in blue, it shows it adding to the left side, and then the Br will be on the more substituted carbon. That's the general pattern you're going to see for addition reactions. The bromine group, the nucleophile at the end, will be attached to the more substituted carbon, the H to the least. You need to know the mechanism to understand this fully. You break the pi bond, you add the H, you generate this carbocation. This then can be attacked by the nucleophile, Br minus plus attracts minus, you end up getting your your alkyl bromide product. Let's look at an energy diagram because this is going to explain the different types of carbocations you can generate. So first of all, I'm going to add the H here on the right so I can have the left side open as a carbocation with a plus charge. So it has 6 electrons and a plus formal charge. It's begging for electron density just to make the full octet. So this is tertiary because it has 1, 2, 3 carbons attached. So a tertiary carbocation is lower in energy and more stable. So it's lower here. It's red on this energy diagram curve. So we start with the alkene. That's lower in energy than the carbocation intermediates because these are overall reactive intermediates. So as you go through these sort of transition states, notice the transition state, these are not isolable. These are just kind of the in-between, on the way between the reactant and this tertiary carbocation intermediate. You can see bonds are starting to break, bonds are starting to form. We show that with little dots, dashed or broken or newly forming bonds. Notice where the secondary carbocation is. If I added the H to the more substituted side, I would have gotten a carbocation on the right side here, which reflects it here as being the less substituted. Less substituted carbocations are less stable, meaning they're higher energy. So it's higher up, more of a hill to reach. It's less of a hill to climb to get to the tertiary. Okay, if you take both of these steps, you've got a hill to climb to get to this carbocation intermediate, and then your nucleophile attacks. These are 2 steps. Go back to that chapter where I talked about the energies. If there's one intermediate, you need a hill to get to the intermediate, then you can go. The second one's a little lower in energy, and then you release a ton of energy to get to the product. So overall, this is exergonic, releasing energy when you go from reactants to products. So my question here is, what step is rate determining? If you look at these, the rate determining one is the slowest one, is the one that's going to be the highest hill. So it's your first step. And it's because you're trying to generate this very reactive carbocation intermediate. Once you get here and the ions find each other, bam, very quickly it'll funnel down to the product. Why is the tertiary more stable, right? I showed you on the energy diagram, but do you understand the main concept why? The reason is hyperconjugation. You've seen this once before in the alkene section. You have hyperconjugation adding into the pi bond of alkenes. That's why more substituted alkenes are higher in, are more stable and lower in energy. So in this case, you have a methyl group next to a carbocation. This is a simple ethyl cation. This carbocation, again, it has 3 substituents, 6 electrons, but it has a p orbital that's vacant or empty, begging for electron density. So if it can share some of the electron density from the CH bond, remember a bond is made of 2 electrons, so there's 2 electrons here, it could donate in and stabilize. The more of these groups you have around to do hyperconjugation, as you go from primary to secondary to tertiary, the more stable you are. The less stable is methyl, the most stable is tertiary. So if you have a preference or an option to form a secondary or tertiary, you will prefer to form a tertiary, same as secondary over primary. Okay, let's practice. Pause, draw a mechanism for the following. So you're going to be using curved arrow notation. And the first thing you're going to do is have the alkene, which acts as a nucleophile. The 2 electrons here are going to attack and form a bond with the H. That means the HBr bond breaks and the 2 electrons in the HBr bond go as a lone pair to form bromide. So the H goes on the less substituted carbon here. So the H in the HBr went here. That means you have a carbocation at this other carbon center here, the more substituted. The next step is this guy is just going to add in, and sorry, I didn't show, I apologize, but I should have drawn an arrow of this lone pair attacking the carbocation to give the bromo cycloalkane product here. So let's practice a couple. Draw the expected major product. Again, these are going to go through Markovnikov addition. Pause and then unpause and we'll go over it. So we're going to add to the least substituted. Adding the H to the least substituted carbocation is tertiary here. You get the bromine there. On the more substituted, same situation. Bromine at the more substituted alkene carbon center. What about stereochemistry? We haven't talked about that. Sometimes there is no stereochemistry that's generated, but sometimes there is. In this case, can you predict the product? You can predict the regiochemistry, which is where the chlorine is going to go. It'll go here on the more substituted carbon, but is it going to be R or S? So this is where understanding the orbitals comes into play. A carbocation is flat. It has 3 groups, so sp2 hybridized, trigonal planar. It's planar flat. So you have this empty vacant p orbital that the nucleophile can come on from the top or the bottom with equal probability. So you could get, in this particular case, both enantiomers. And it's in equal amounts, so we call that a racemic mixture. You could get R and S. The other thing that we need to talk about is carbocation rearrangements. So to do that, I need to introduce the Hammond postulate. The Hammond postulate basically explains why the stability of the carbocation affects the rate of its formation. So I already told you tertiary is more stable. Why is that going to affect what type of product is formed? So let's look at this. The Hammond postulate says related species that are similar in energy are similar in structure. And the structure of the transition state resembles the structure of its closest stable species. So I'm going to explain that. let's look at our two basic energy diagrams: endergonic, overall requiring energy; exergonic, overall releasing energy. So in this case, this is showing in the endergonic example, the product, because it's higher in energy, is closely resembling the transition state. So these will be similar, more similar in energy and structure. In the exergonic case, the reactants and the transition state resemble each other more. Okay, how does this apply to carbocations? Basically, the carbocation is a higher energy intermediate, and if you just take a snapshot, it's going to be considered our product in this case, so it'll resemble this endergonic transition state or endergonic reaction. So basically, the carbocations are higher in energy and closely resemble the transition state. Remember, this transition state is something in between, but it'll more closely resemble these. So the whole point of this is underlined here. Things that stabilize the product, the carbocation, will also stabilize the transition state leading up to those products. We just talked about hyperconjugation. Hyperconjugation stabilizes carbocations. So they're going to stabilize those transition states and lower the energy, allowing you to achieve that faster. Okay, let's talk about carbocation rearrangement. First, can you predict the product? I'm going to tell you though, if there's some sort of rearrangement, if you can move an H, or even if there's no H, you can consider moving an alkyl group like a methyl group to produce a more stable carbocation, that will occur. So let's look at this. I'm going to add an H, kick out a chloride to give me my secondary carbocation in a Markovnikov fashion. Secondary is pretty good, but tertiary carbocation is even better. So if you're in a situation where you can move an H to create a tertiary carbocation, that's going to happen. So in a normal case, you get this. You get a racemic mixture that's about stereochemistry, but you get this. But that's not the only thing you're going to get. What you can also get is something called a hydride shift. So starting here, there's a hydrogen off this carbon, and this guy can just move its whole bond over. So this bonded H will slide over and fulfill the octet here and reveal a carbocation where it just left, creating a tertiary. So the biggest question I get is, when does this happen? Basically, would you ever go secondary to secondary? No, you don't need to do that. It's mainly going to happen when you can convert a secondary carbocation to a tertiary. If you're in a situation where you do have a primary carbocation, you would also prefer to make a secondary. It's hard to form primary carbocations in the first place, so that's not the most common example, but mainly you're going to find this with secondary going to tertiary, and then the chloride can come in and generate this newly arranged product. So at the end of the day, if you ran this reaction, you would get both of these. Just to let you know, there are cases where you might not have a hydrogen. If the hydrogen is present, move the hydrogen. But sometimes you might have just alkyl groups. You can also move an alkyl to reveal a tertiary carbocation, to go from secondary to tertiary. Okay. Again, you would get a mixture if you ran this reaction. So just to be upfront, this isn't the cleanest type of reaction to occur. A lot of times the dilemma for the chemist is designing reactions that are going to be clean, that are going to give the products they want in high yields. Now it's time for you guys to practice. You guys are going to predict the products for these three. And I already wrote the products there. So maybe you can cover it with a sheet of paper. I totally messed that up. Sorry. So erase these and predict the products hold up a paper so you don't see those and predict the products. And then do the last one, which is something you've seen, but we're doing it with HBr. I challenge you to write a mechanism for part C. Okay, so for A, you would add the H to the least substituted side. The chlorine is going to go here, as you see in this product. For this compound in B, again, you add the H to the least substituted in a Markovnikov fashion. So the bromine goes here, which is through a tertiary carbocation. So normal Markovnikov addition, no funny business. This one, make sure you pause and try the mechanism on your own, because that's something you would have to do. And I'll show you now. The H is going to add to the least substituted carbon, forming a secondary carbocation here. So I would have drawn an arrow to the H and kicked out the bromide. I did not show that. And then you'll have a 1,2 hydride shift. The reason is you generate a secondary carbocation, but you can create a tertiary. So this is similar to the example I gave. You're going to do the 1,2 hydride shift. And I'm hoping that you guys drew this yourself. You'll need to be able to do that on an exam. And then on this tertiary carbocation, your bromide will come in and give your bromide product. Okay. Let's do one final problem. And this is asking you to not predict the product. I'm giving you the product. So you are to draw a mechanism for how to get here. Here's my tip for you. You have 2 methyl groups on this carbon at top, but here it's rearranged. So the first thing you want to think of is after you create your first carbocation, consider a 1,2 hydride shift if that's possible to generate a better carbocation. If there's no H to move, then a 1,2 alkyl shift. Okay, pause this, spend some time, and then unpause and I'll go over it. You'll add the H, and you could have added it to either carbon. I'm showing the secondary carbocation here on this side. This also allows you, or this also shows you kick out the chloride, but I'm doing it on this side because to get to the product, you have to do a 1,2 alkyl shift. There is no hydrogen here. If there was a hydrogen, I would have preferred to move the hydrogen. That's easier. But here I can move a methyl to reveal now a tertiary carbon here on the center. So notice the alkyl group moves to this center here. That's why I moved the methyl here. And now I only have 1 methyl up top. A carbocation, now tertiary, which is better. And then the chloride is going to come down to give you this chloro dimethyl cyclohexane. Okay, this is where we end. And we'll do more on alkene chemistry in chapter 8.